Okay, so we know what uncertainty is. It's something that goes along with every single measurement. Every single measurement has uncertainty, right? Why? Because, well, there's every single device. One way to look at it, why does every measurement have uncertainty? Every single device has some limit to its precision. If you get the best ruler in the world, right? The best ruler, and you measure the length of your, of your arm, you might say that this is 24 point, and this is the best one in the world, right? 6, 7, 5, 1, 9, 9, 2, 8, 4, 3. But even the best in the world, the best ruler in the world, is going to stop at some point and say that's how many centimeters. That's the length of your arm in centimeters. Oh, this is not a very long arm. This is weird. 124. No, now your arm is too long. Well, anyway, the point is that you can't go on forever with decimal places. And so you don't know what these extra places are. You have no idea. So every measurement that we take, because we use a device that's not precise infinitely, because these decimal places can't go on forever, just devices, it's impossible to build a device that measures every single decimal point forever. So because of that, every single measurement has at least a little uncertainty. Specifically, the uncertainty is in these last digits. We don't know what those are. Okay. If measurements have uncertainty, then if you take two measurements, like let's say you take the height of your arm, the length of your arm, and you add it with the length of your, the length of your body to get the total length of your arm plus body equals L total. Well, you got a little bit of an issue here, right? Because this has uncertainty because it's a measurement. This has uncertainty because it's a measurement. So surely this value has uncertainty too. And yes, it does. It has uncertainty as well. So we have to account for the uncertainty. How do we combine the uncertainty here with this uncertainty, right? Arm and body, those two uncertainties. I could call it arm if I wanted, and body here. How do we combine those to get the total uncertainty in the total value, right? And how is the rule different? What if we subtract? What if we do A minus B? And those are two, but both of these are measurements. What if we do A times B, or A divided by B, right? Or what if we do A and we raise it to the power of B, where A is the measurement, B is just a number? We're going to learn now the rules for propagating or carrying forward our uncertainty. Okay, first the rule for addition and subtraction. Here's the rule for addition and subtraction. Okay, here we go. This right here is your data booklet for IB Physics. When you take the IB Physics exam, you get everything in this book. You get all of these constants, including, where is it? Speed of light, 3 times 10 to the 8. Right? Here it is. Let me zoom in. 3 times 10 to the 8 meters per second. You even get the value of g at the surface of the Earth, 9.81 meters per second squared. The value of big G, you all remember that. And a bunch of equations, too. You even get the prefixes, right? Like milli is 10 to the minus 3. And you get a bunch of equations. Some conversions, what circuit components, circuit symbols, and some equations. The equations are organized by topic. This is topic 1 that we're learning right now. Topic 2 is the stuff we learned last year in honors physics, or chem phys. And so let's take a look. Let's take a look at these. The first equation under uncertainties and errors, if y is equal to a plus or minus b, right? So if you take two measurements, a and b, if you add them or subtract them, then here's the uncertainty rule. The absolute uncertainty in y equals the absolute uncertainty in a plus the absolute uncertainty in b. So let's unpack this a bit. We're going to use the same notation. Let's say you have two measurements, a and b, and y is equal to a plus b, right? And these are measurements. Y is not a measurement, but it's something you acquire from two measurements. The absolute uncertainty in y equals the absolute uncertainty in A plus the absolute uncertainty in B. And let's say that instead of adding the two, you do A minus B. Subtract one from the other. In this case, the absolute uncertainty in y is equal to the absolute uncertainty in A plus, not minus, but plus the absolute uncertainty in B. So no matter if you add or subtract the two measurements, you still add their absolute uncertainties. Right, here's an example. Let's say you have, you measure a first length is 5.0 plus or minus 0.3 meters. A second length is 3.0 plus or minus 0.1 meters. Notice, by the way, that I've given my absolute uncertainty 1 sig fig, and I've rounded the measurement to the same place. Kind of looks like a smiley, right? Some eyes. There we go. It's a person. Okay, where are we? What's going on? So, let's say you want to take L1 and you subtract from it L2. Well, you get 5 minus 3 is going to be 2.0. I was careless. I should have written this as 5.0 for sig figs. And what's delta L going to be? And this is, let's call this L3. What's the absolute uncertainty in this value? L3, which equals 2, and I've left off units, 2 meters it should be. What's its absolute uncertainty? Well, the rule says take the absolute uncertainty in L1, add it to the absolute uncertainty in L2. So it's 0.3 plus 0.1, 0.3 meters plus 0.1 meters, and that gives 0.4 meters. And it's uncertainty, absolute uncertainty, so we should write plus or minus. Like that. There we are. If you had added L1 with L2, you would get a different value for L3, but the uncertainty would still be the same. Okay, that's the rule for adding two measurements A and B. Let's look next at the rule for multiplying and dividing. Look at this. If you have three measurements, A, B, and C, whether you multiply them together or divide them, you always add together. Here's A, here's B, here's C. Here's the percentage or fractional uncertainty in A, the fractional uncertainty in B, and the fractional uncertainty in C. And that together gives you the fractional uncertainty in Y, the new quantity. So again, okay, multiplying and dividing. Multiplying and dividing. Whoops. Okay, if y is equal to a measurement A times a measurement B, then you could say the fractional uncertainty in y, or, yeah, let's do it fractional, equals the fractional uncertainty in A plus the fractional uncertainty in B. Another way to think about this is to say the percentage uncertainty in y is equal to the percent uncertainty in A plus the percent uncertainty in B. Okay. Oops. And there's no formal notation for percentage uncertainty, so we kind of make up a notation, and this is the notation I like to make up. Now, the way it works out, if you say y, if you acquire y by taking A and dividing it by B, then believe it or not, you use the exact same rule. Whether you add or subtract, whether you multiply or divide, you can multiply or divide two measurements, and in both cases, you use this rule. In fact, if you want to take, y and make it a times b over c, then to get the uncertainty in y, you would use the percentages and add the percentages, right, for all three. Okay, and this is basically the rule that the data booklet, your equation sheet, that the data booklet shows, right there. They've chosen to express it in fractional form, not percentage, but it's the same rule. Okay. So let's say you measure a square. No, a rectangle, not a square, it's a rectangle. And this side is 4 meters plus or minus, let's say, 2%. And when I say plus or minus 2%, I mean 2% of 4. And this side is 3 meters plus or minus 6%. What's the area and the uncertainty in the area? Well, the area is length times, let's say, base times height. So 3 meters times 4 meters. That's 12 meters. And the percentage uncertainty in A is what I can find straight away. Percentage uncertainty is going to be, well, you just add the percentage uncertainty in base plus the percentage uncertainty in height. Whoops. Plus the percentage uncertainty in height. That's what, 2% plus 6%, which yields 8. Now let's say that you next want to find the absolute uncertainty. And this, you could write this, we probably should write this as plus or minus, by the way. Alright, and next we want to find the absolute uncertainty in the area. How do you do that? Well, you've got the percentage uncertainty. You've got the area itself. So how is absolute, percentage, and measurement, how are those all related to each other? The answer is the percentage. We said that the percentage is just the absolute over the area itself. Now, when you solve this equation for delta A, for the absolute uncertainty, by the way, we use a delta symbol for two things. Here it means absolute uncertainty. In other contexts, it means change in. So delta has two meanings as well. Okay. When you plug in and solve, you have two choices. You can either use the equation the way I've shown, and then convert your 8% to a decimal before you plug in. And this would be the unknown. What's the measurement? Or what's the value of base? 12 meters squared. Oh my gosh, I left off the squared. I was so focused on other things. That's okay. I'll just tell myself, don't forget to leave off the squared when you do units for area. Okay, so you can calculate the delta A this way, express it as plus or minus, 0.48 meters squared. Or, instead of converting the percentage at the onset, you can use this equation. Plug in your 8%. See how I haven't converted this time? I'm just putting in 8, not 0.08. My unknown is the absolute uncertainty in area. True area is 12 meters squared times 100%. The percents will cancel out, just like units would cancel, and you can solve and you'll get the exact same answer. Okay, one final rule, and this is pretty quick. It's exponentiation, which I assume is a real word, meaning it's the verb form of exponent, or to take as an exponent, to exponentiate. Don't look it up on Google, because it's probably not really a word. Okay, if y, here it is, here's that rule. If y is equal to a to the n, then the fractional uncertainty in y is equal to the absolute value of the fractional uncertainty in a times the exponent, n. So let's see an example. This is tricky. We can write the rule down if we want. When y is a to the n, and in this case, only a is a measurement. A is the measurement, and n is a definite value. Let's see, what's the word? Let's just say it's a value with no uncertainty. It's just a number like 2, like a squared, but it has no uncertainty. Okay. Then the rule is the fractional uncertainty in y is equal to the fractional uncertainty in a, but then times whatever the exponent is, and also make it positive. Okay. Take a moment, pause the video, see if you can rewrite this using percentage uncertainties. Right. Rewrite this using percentage. Identify where percentage uncertainties are in this equation. Okay, I assume you paused the video. Here's what we can say. Percent uncertainty in the new value is equal to the percent uncertainty in the old value times the exponent that we used. Here's an example. Y equals a squared, where a is 5.0 plus or minus 0.5 grams. By the way, grams, that's not the fundamental unit of mass. The fundamental unit is kilograms. It's the only one, mass is the only one unit whose fundamental unit, mass is the only quantity whose fundamental unit has a prefix kilo. But we haven't measured it in the fundamental unit, we're just measuring it with grams, not the fundamental unit of kilograms. Okay. And they ask, what's the percent uncertainty in y? What's the absolute uncertainty in y? Well, the absolute uncertainty, we're going to need the value of y to find this. Percent uncertainty, we use our rule, right? So percent uncertainty in y, because we get y by squaring a, percent uncertainty in y is that same exponent 2, I've moved it right to here, times the percent uncertainty in a. That's going to be absolute value of 2 times, well, a is 0.5, the percent uncertainty in a is 0.5 grams over 5 grams. The grams, of course, cancel out. 0.5 over 5, well, if I multiply the numerator and denominator by 2, that's going to be 1 over 10. And then I multiply it by this 2 over 10. So this we could call this 1 over 10 if we simplify, reduce. And then 1 over 10 times 2 gives us 2 over 10. So the answer is 2/10 or 20%. To get the absolute uncertainty in y, well, we're going to need more information. We need y. We need the percentage uncertainty in y. Right? Percent is absolute over value. We know percent uncertainty. We're looking for absolute uncertainty. So first we find the value of y, so we can plug it in and calculate delta y. So what's the value of y? Well, it's just a squared. See this? Y is a squared, which is 5 grams squared. So y is 25 square grams. This is a strange idea, but let's plug that in. 25 grams squared. equals the percent uncertainty, and I'm going to convert to 0.20, and I'm not going to put times 100%. I'm not going to do this because I've already converted from the percentage to a decimal. So that's what I prefer to do personally. You solve for delta y, and what do you get? Well, this is 1/5. So 1/5 of 25 is plus or minus 5. So the uncertainty in y is plus or minus 5 grams squared. Now, remember how we said earlier that y was 25 square grams? The way we usually express our final answer with this sort of thing, one of the ways we can, is by saying y is equal to y and its uncertainty is 25 grams squared plus or minus 5 grams squared. And after we do that, we have to check and see, have we rounded everything correctly? Yes, this has 1 sig fig, and yes, they are both rounded to the same place, which is the units place in this case. Now, I want you to spend some time working on this practice. I want to point out just very, very quickly, number one, you see that we have an equation, but to find the what we're actually calculating is S1. We're not calculating S total, we measured S total. So we measured S total, we measured S2, and we're calculating S1. So before I do anything else, I'm going to isolate S1 so I know what types of rules I need, what types of uncertainty rules I need to use. Now that I've isolated S1, I say, oh, okay, I'm taking two measurements. These are both measurements that we know. I'm subtracting one from the other. And so whenever we subtract, you can say the uncertainty in S1, the absolute uncertainty in S1, is the absolute uncertainty in S total. Ooh, subtraction, we still add the absolute uncertainties. That's the weird rule. Whether you were to add these or subtract, it would be the same rule here. Okay, so take a moment and take some time here, and you all are going to complete these uncertainty problems. So numbers 1 through 4, then on the next page, 5 through 8, then all the way down to 12, right? Any more after that? Oh, you get to go all the way to 15. Yeah, go to 15. Now the last thing I want to say, this has been somewhat of a longer video, which I know is tasking, and we're combining lots of different rules into this one video, and you have to distinguish in your practice. You have to be able to say, okay, which rule am I using? Am I using the multiplication rule, or the subtraction rule, or the exponentiation rule? While that will make this is going to make your practice harder, okay? The fact that we're combining all this together, I've done that on purpose, and the reason I wanted to mix it together is because this is going to make it, you're going to be better at the end of this practice. You're going to be better at remembering the different rules and distinguishing them from each other. The practice here is going to force you to think about those distinctions. So try to memorize these rules at the onset of your practice. And then, after you memorize the rules, right now, just real quick, say, okay, this is a problem, number one, this is a problem about subtraction. The subtraction rule is this, not this. That's the rule for multiplication. So I don't want to use that one. I want to use the rule for subtraction. So go through that process, quiz yourself, try and do this without looking back, because if you practice memorizing it, then this practice here will all serve, this practice is all going to serve as like flashcards for the rules themselves, right? Which is good. That'll help you get even better. Okay, good luck.